Now we are seeing a problem from the topic gas turbines. Let us see the problem. In a constant pressure open cycle gas turbine, air enters at 1 bar and 20 degrees centigrade and leaves the compressor at 5 bar. Temperature of gases entering the turbine is 680 degrees centigrade and pressure loss in the combustion chamber is 0.1 bar. Efficiency of the compressor is 85%. The efficiency of the turbine is 80%. And gamma is 1.4 and the Cp is 1. Very specific heat is 1.024 kilojoules per kg Kelvin for air and also gases. And also here take the efficiency of combustion is given 85%. And here we have to find the quantity of air circulation if the plant develops 1065 kilowatts power, and also heat supplied per kg of air circulation, and also the thermal efficiency of the cycle or the plant. And here is giving mass of the fuel may be neglected. So here if you see the given data, first of all if you observe a TS diagram for this gas turbine cycle showing here and these different points locating the cycle, gas turbine cycle, and here one is the entrance point, the air enters the compressor. 1 to 2 is the compression process, 2 to 3 heat addition, and 3 to 4 expansion. And so open cycle, here you can just assume a continuous line or a dotted line, you can take like that. And here if you see P1 is given 1 bar and P2 is 5 bars. So means here after compression point 2 is that is P2 is 5 bar, and P3 if you see P3 is the after heat addition process, means after it is air leaving the combustion chamber. So there is a third point, it is 4.9 bar. How means so P2 is 5 bar and is given there is a pressure loss in the combustion chamber, and that is 0.1 bar pressure is lost in the combustion chamber. So this point 2 is the input, or 2 dash is the input to the combustion chamber. So at this point the pressure is 5 bar, and this 2 to 3 represents the combustion process or heat addition process. So there in the combustion chamber 0.1 bar pressure loss is there. So after leaving the combustion chamber the pressure is reduced to 4.9 bar. Why means 5 minus 0.1 bar is nothing but 4.9 bar. So that is the pressure at point 3, that is before to the point before to the turbine, you can take like that. And also if you see and here you can take this P4 is 1 bar. So once again this is a constant pressure line and this is a constant pressure line, or it's open cycle gas turbine is given. So that is once again the fourth point is nothing but it is a atmospheric pressure, that is 1 bar. So you can take anyway. And here the initial temperature is given 20 degrees centigrade, or it is 293 kelvins. And T3 the temperature of gases entering the turbine. So point 3 is the point where the point entering to the turbine. So because 3 to 4 or 3 to 4 dash is the expansion process, so point 3 is the point which is entering to the turbine. So the temperature is given 680 degrees centigrade, or it is 953 kelvins. And efficiency of the compressor is given 85%, turbine is 80, and also efficiency of combustion is 85%. So you can take efficiency of compressor 0.85 and turbine 0.8, and also efficiency of the combustion you can take 0.85, and Cp value is given 1.024 kilojoules per kg Kelvin, and the gamma 1.4. This is for air and gases. So air and gases means here, so at the point air is entering and point 2 also air. Now at the point you can see the point is it is a air fuel mixture, so they form gases. So at point 3 you will get gases. So for those two air and gases the Cp and gamma values are given, and he is told to take same values. So power developed is given 1 power developed is given 1065 kilowatts is given. So here we are supposed to find out the quantity of air circulation with the given power, and heat supplied, and also thermal efficiency of this cycle or plant we have to find out. So here we'll find out the quantity of air supplied by using the power formula. So you can write power formula as MA into W net, and W net you can find out W turbine minus W compressor. From that you can find out quantity of air circulation, and heat supplied you can find out from the combustion formula. You can write a efficiency of combustion formula, that is heat taken by the burnt gases by the actual heat supplied by the fuel. From that you can calculate the actual heat supplied per kg of air circulation. And as a thermal efficiency, you can find out the W net work output to the heat supplied. So from those formulas you can find out all these quantities. So yes, friends, if you are new to my channel, please subscribe to my channel and activate bell symbol for more videos and updates. And also please share my videos with your friends. So anyway, I told in the first bit we have to find out the quantity of air circulation. So here I told this can be find out with the power formula. So you can write power is MA, means M dot A, that is a mass circulation per unit time, so that is kg per second, that we have to take here MA. And W net, with this formula you can find out, and W net you can find out the formula, it is W turbine minus W compressor, and W turbine is given by the formula Cp into T3 minus T4 dash, and W compressor is Cp into T2 dash minus T1. So friends, for the explanation of these formulas, please refer my previous video on problem 1 on gas turbines. So by using these formulas you can find out W net, and here suppose if you want to find out W compressor work input to the compressor, Cp is given and T2 dash you have to find out, T1 is given, T2 dash you have to find out. And also for W turbine you have to find out T4 dash, T3 is given. So first of all here you have to find out T2 dash. So to find out T2 dash, first of all you know what is T2 value. So why? Because T2 dash you can find out from the formula, that is isentropic efficiency of the compressor is given by this formula. So here also for this formula and isentropic efficiency of turbine formula, also just refer my previous video. That's the problem 1 on gas turbines. So anyway, from this formula you can find out T2 dash. So for that you require T2. So for to find out T2, just we are considering the process 1 to 2. The process is reversible adiabatic process. If you see this process 1 to 2 is a reversible adiabatic process, isentropic process. So we know for adiabatic process you can write the relation between temperature and pressure between points 1 and 2. You can write T2 by T1 is equals to P2 by P1 whole to the power of gamma minus 1 by gamma. So here P2 is given 5 bar and P1 is given 1 bar. So and gamma is 1.4. So when you simplify that, we are getting this as a 1.584. That is the ratio between T2 and T1. So from this you can find out T2 is 1.584 into T1, and T1 value is 293. So when you simplify this, we are getting T2 value as 464 Kelvin. So I told we'll use that T2 value in this isentropic efficiency of compressor. So it is given by this formula T2 minus T1 by T2 dash minus T1, and this isentropic efficiency of the compressor is given 0.85, and T2 464 we got just now, and it is a 293. It is T1 value. T2 dash you have to find out, and it is once again 293. So when you just rearrange here, you can write like this, and when you substitute these values, so we are getting T2 dash as 494 kelvins. And also here we have to find out T4 dash also. So to find out T4 dash, once again here we require T4 value. T3 is given, and efficiency of turbine also given. So here we require T4 dash. So this T4 dash, before that we have to find out T4. So to find out T4, once again we are considering the process 3 to 4 here. So this process 3 to 4 is also a reversible. 3 to 4 is also a reversible adiabatic or isentropic process. So for we know adiabatic process, you can write the relation between temperature and pressure T4 by T3 is equals to P4 by P3 whole to the power of gamma minus 1 by gamma, and P4 I told it's a 1 because it is open to atmosphere. So 0.4 is open to atmosphere, means it is, you can take it as a 1 bar, and also P3 we have seen it is a 4.9 bar. So here you can observe it is P3 point is 4.9 bar. So when you substitute there and when you simplify, gamma is 1.4. So that values we are getting 0.635, and it's a T4 by T3 0.635, and we require T4, it is T3 into 0.635. T3 is given 953 kelvins, and if you simplify that, we are getting T4 value as 605 Kelvin. And here from this we have to find out T4 dash. So for that we are using the formula isentropic efficiency of a turbine. So that is given by the formula T3 minus T4 dash by T3 minus T4. So this isentropic efficiency of turbine is given 80% or it is 0.8. T3 is 953 is given, minus T4 dash we have to find out. Once again it is T3 953 and T4 we have just find out it's 605 kelvins. So when you just rearrange and when you simplify this, we are getting T4 dash as a 674.6 kelvins. So after that is told we have to find out here the work input to the compressor. So it is given by the formula Cp into T2 dash minus T1, and Cp value is given 1.024 and T2 dash we got here 494 and T1 is 293. It is given value, and if you simplify that we are getting work input to the compressor is 205.8 kilojoules per kg of air. And also WT work developed by the compressor is given with the formula Cp into T3 minus T4 dash. Cp is given 1.024 and T3 is also given 953 kelvins, and T4 dash just we have find out 674.6 kelvins. So when you simplify that we are getting WT work developed by the turbine as a 285.1 kilojoules per kg of air circulation, and here we require W net, it is W turbine minus W compressor. So it is 285.1 minus 205.8, and when you do that we are getting W net as 79.3 kilojoules per kg of air. And here we require mass of air circulation cycle. If the mass of air is flowing is MA, that is in kg per second, the power developed by the plant is given with the formula P is equals to MA dot, that is kg per second in terms of kg per second, and W net. So power is given 1065 kilowatts, and this is kg per second, and this is 79.3 kilojoules per kg Kelvin, sorry, kg kilojoules per kg. So if you see, just if you tally here the units, so MA is kg per second, and this is kilojoules per kg. So this kg goes, and this is kilojoules per second, there is nothing but kilowatts. So here this we have substituted in kilowatts, so it is satisfied. So anyway, from this you can write MA is 1065 by 79.3. So when you simplify that, we are getting mass of the air circulated as 13.43 kg per second. So this is the first bit, and second bit we require heat supplied per kg of air circulation, and for that we can use the formula, or we can use this formula, is efficiency of combustion. You can write as a heat taken by the burning gases by the actual heat supplied by the fuel. So from this, once again, if you write actual heat supplied by the fuel is equals to heat taken by the burning gases is given by the formula Cp into T3 minus T2 dash. So here we are neglecting the mass of the fuel, and here we are taking or we are calculating this heat taken and heat supplied per kg of air. So simply you can write heat taken by the burning gases formula Cp into T3 minus T2 dash, and here you have just rearranged here. So efficiency of combustion we have taken eta Cc as a notation. So Cp is given 1.024 and T3 is given 953 kelvins, and T2 dash we have find out 494, and efficiency of the combustion is given 85% or it is 0.85. So when you simplify that, we are getting heat supplied, that is actual heat supplied is 552.9 kilojoules per kg of air. I told we are calculating per kg of air. So here next bit we have to find out the thermal efficiency of the cycle. So the thermal efficiency formula is given by the work output per kg of air and heat supplied per kg of air. So work output W net we have find out 79.3 kilojoules per kg, and also heat supplied just we have find out 552.9 kilojoules per kg. So when you simplify that, we are getting it as 0.1434, or in terms of percentage means you have to just multiply with 100, that is thermal efficiency of the cycle is we are getting 14.34%. So this is a way to solve this kind of question. So don't forget to subscribe and activate bell symbol, and also share my videos with your friends. Thanks for watching.